Eureka! This unit is divided into 10 programs. The program you're about to see is on inertia. Then program 2 looks at mass. Next comes speed. This is followed by 2 programs on acceleration. A program on gravity. Then one on weight versus mass. Then work. And finally, 2 programs on energy itself. Kinetic energy and potential energy. But our story begins with inertia. Physics is about movement, how things move and why things move. Here is a very large thing. What do you notice about it? It's not moving. Go ahead and try and move it. You can't. It doesn't want to move. Is that because it's so large? Try and move a smaller thing then. Well, you managed to move that a little way, but it was a great effort. It was as if it still didn't want to move. Even tiny things are reluctant to move. Even a pebble takes some effort to shift. This is the first rule of physics. Things like to stay where they are. Unless there is some force to push or pull it, no object in the universe will start moving of its own accord. It's as if all objects were lazy. But why is physics about movement if nothing wants to move? The answer is that there are lots of things in the universe that pull or push on objects and force them to move, whether they want to or not. You force the pebble to move. And since things are lazy, you'd expect your pebble to try and stop moving as soon as possible, wouldn't you? Well, you'd be wrong. Strangely enough, although when the pebble was at rest, it wanted to stay at rest. Now that it's moving, it wants to keep on moving. In fact, it would like to keep on moving forever and ever. The only reason it slows down and eventually stops is because things in its path force it to stop. The resistance of the air, or a tree it bumps into, the roughness of the ground. But if there were no air or rough ground or trees to get in its way, if you were in outer space, for example, when you kicked your pebble, it really would go on moving forever and ever. It would never stop. So how can we say that objects are lazy? If the pebble's moving, it's not being lazy, is it? Yes, it is. It takes just as much effort to stop moving as to start moving. You get a feeling for this when you're ice skating. When there's hardly any resistance to your movement and it's easier to keep on gliding along than to stop. The same goes for the pebble. If nothing gets in its way, if nothing helps it to stop, it will have to make all the effort to stop by itself. And it's much too lazy to do that. We can now modify the first rule of physics from things like to stay where they are to things like to keep on doing what they're already doing. If a thing is at rest, it wants to stay at rest. If it is moving, it wants to keep on moving. In other words, there is lots and lots of laziness in the universe. Physicists have a special word for laziness. It comes from Latin. Inertia. Eureka! The story so far. Things like to keep on doing what they're already doing. They don't like to start moving or stop moving. They are lazy. Another word for laziness is inertia. And now, mass. A large thing is equally difficult to move and to stop moving. Whereas a small thing is easier to move and easier to stop moving. The big rock has more inertia than the little rock. It is lazier than the little rock. Are all big things lazier than little things? Does inertia always increase with size? Oh, really? Well, why don't you take a huge cube of styrofoam and try to throw it? And catch it. Then do the same with a small cube of lead. Do you still think big things are lazier than little things? The small cube of lead was more difficult to stop moving than the big cube of styrofoam. In this case, the small thing was lazier. It had more inertia than the big thing. So inertia doesn't always equal size, or volume, or bigness. In fact, when we talk about how much inertia a thing has, it isn't really a question of how big it is, but of how massive it is. A massive rock, for instance, is a rock that contains masses and masses of stuff or matter. It's not merely big, but also solid and chunky, like a massive bulldozer or a massive ball player. You don't push things like that around very easily, any more than you can stop them easily when they come charging at you. They are too massive. Because of this, scientists took the word mass as a measure of inertia. The more the mass, the more the inertia. In spite of the fact that the styrofoam cube looks much bigger and more important than the little lead cube, it doesn't contain as much stuff. There's much less to it than there is to the lead cube. It has a far smaller mass. But just how much is a lot and a little when you're talking about mass? To find that out, we have to go to a place called Sèvres, near Paris in France, where a particular piece of platinum has been very carefully preserved. Scientists all over the world have agreed to call this little chunk of metal 1 kilogram, which is very convenient, because if you take a balance and put this piece of platinum on one pan and put any object you like on the other, a pebble, let's say, then if they balance exactly, you know that the pebble has a mass of exactly 1 kilogram. But what about the cube of lead? That feels as if it has a lot more mass than the 1 kilogram pebble. Well, all we do is put the cube in one pan of the balance, have a whole lot of copies of the platinum kilogram made up, pile these standard kilograms in the other pan until they balance the lead cube, and then count how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 18, 19, 20. There! Now we know that the lead cube has a mass of exactly 20 kilograms. Of course, we can do the same with the big important-looking cube of styrofoam. 1, 2... Sorry, you have only 2 kilograms of mass. So the lead cube has 10 times more mass than the styrofoam cube. Which explains why it's 10 times more difficult to push around. Eureka! The story so far. Inertia means laziness, the tendency things have to keep on doing what they're already doing. Big things aren't always lazier than small things. It all depends on how much mass they have. The more the mass, the more the inertia. And now, speed. Here is a red ball. And here is a blue ball. Although they're both the same size, the red ball has exactly twice the mass of the blue ball, which will take more effort or force to throw. The red ball or the blue ball? Of course, because it has more mass and therefore more inertia. And the only way to overcome inertia is to use force. But how much more force will it take to throw the red ball? Try it and see. First, the blue ball with 1 kilogram of mass. Then the red ball with 2 kilograms of mass. Exactly twice as much force, as a matter of fact. If you double the mass, you double the force needed to make it move, or to make it stop moving. In other words, if the inertia is doubled, the force needed to overcome it must also be doubled. But what if you pitch the red ball, say at a speed of 20 kilometers an hour, and then pitch the blue ball at twice that speed, at 40 kilometers an hour? Are you still putting twice as much force into pitching the red ball as into pitching the blue ball? Of course not. You'll be putting exactly the same amount of force into pitching both. Why? Because the difficulty of making a thing move not only depends on how much mass it has, but also on the speed at which you want to make it move. Or rather, on how much you want to change its speed. Doubling the mass doubles the force, and doubling the change of speed also doubles the force. Suppose that changing the speed of the blue ball from 0 kilometers an hour to 20 kilometers an hour requires 1 unit of force. Then getting the same ball to go from 0 to 40 kilometers an hour will require 2 units of force. But we also know that it requires twice the force to get the heavier red ball up to the same speed as the lighter blue ball. Therefore, getting the blue ball up to 40 kilometers an hour requires precisely the same amount of force as getting the red ball up to 20 kilometers an hour. Naturally, all this also applies to catching a ball to stopping it moving. It will take as much force to stop the lighter blue ball going at 40 kilometers an hour as to stop the heavier red ball going at half that speed. Force varies with mass and change of speed. This tennis ball has a mass of about 50 grams. This cannonball has a mass of about 20 kilograms, or 20,000 grams. Obviously, the cannonball has more inertia than the tennis ball. It will take much more force to make it move or to make it stop moving because of its enormous mass. But now look at what effect speed can have. If someone serves the tennis ball at you fast enough, it can knock the racket clean out of your hand. Whereas, if the cannonball dribbled out of the cannon slowly enough, you would be able to catch it quite easily. Stopping something means changing its speed. It can take more force to change the speed of a fast tennis ball than to change the speed of a slow cannonball. Change of speed makes a big difference.
Eureka!
The story so far. The tendency things have to keep on doing what they're already doing is called inertia. Mass is a measure of inertia. But in order to make a thing change what it's doing, you have to use force. And force varies not only with mass, but also with change of speed. And now, acceleration, part 1. If you wanted to exert as little force as possible, which of these two bikes would you choose to ride? No contest. The modern racing bike has much less mass than the old-fashioned bike, and therefore much less inertia. So you'll need less force to make it move. But wait, is that all that force is proportional to? To mass? Isn't there something else? Yes, change of speed. Mustn't forget that. Force is also proportional to change of speed. If you want to reduce the force you put into pedaling, you're better to go from 0 to 25 kilometers an hour than to try to zoom up to 50 kilometers an hour. Too easy, you think? Well, go on then. Ride the bike at 25 kilometers an hour. Stop. That wasn't 25 kilometers an hour. You weren't even doing 5 kilometers an hour. That's right. It takes time to reach the speed you want to go at. In the first second you start pedaling, you'll be lucky to get up to 3 kilometers an hour. After the second, you may reach 6. After the third second, 9, and so on. It'll probably take you 8 seconds or so to reach 25 kilometers an hour. Let's look at that again. That's it. Now you're going at your top speed. Is this when you're exerting maximum force? You think so? Well, take your feet off the pedals then. You're hardly losing any speed at all, are you? You're exerting zero force, and yet if it weren't for the bumpiness of the road and the wind resistance slowing you down, you'd still be going at 25 kilometers an hour. Why? Because of the first rule of physics. Things like to keep on doing what they're already doing. It isn't the speed of 25 kilometers an hour itself that requires effort or force from you. It's getting up to that speed. That's why we say that force varies with mass and change of speed. But the more quickly you change your speed, the more force you'll have to exert. If making your bike go from 0 to 25 kilometers an hour in 8 seconds requires 1 unit of force, then making it go from 0 to 25 kilometers an hour in half that time, in 4 seconds, will require 2 units of force. The thing is, we're not just talking about change of speed, but about an increase of speed in a certain time. In other words, we're talking about rate of change of speed. So we should say that force varies with mass and rate of change of speed. But that's a very long sentence, so we shorten it by using the other word for rate of change of speed: acceleration. Force varies with mass and acceleration. And we can shorten that still further by turning it into an equation. Force equals mass times acceleration, which just so happens to be the second rule of physics. This should be obvious to cyclists, and even more obvious to motorists, who are always going on about acceleration. But what about a baseball pitcher? Does he need time to get the ball up to its top speed? All right. Pitch that ball at 50 kilometers an hour. Freeze. It isn't going at 50 kilometers an hour at this point. More like 10 kilometers an hour. This is just the beginning of your wind-up. A bit later, the ball may reach 20 kilometers an hour, then 30, then 40. But it's only at the last split second as it leaves your hand that it reaches its top speed. The fact is, you don't so much pitch a ball at 50 kilometers an hour as accelerate it up to 50 kilometers an hour. That's what your wind-up is for. You may call yourself a baseball pitcher if you wish, but in reality, you're a baseball accelerator.
Eureka!
The story so far: the greater the rate of change of speed, the greater the force required. Another word for rate of change of speed is acceleration. The more you accelerate, the more force you need. But force also varies with mass. So we say that force equals mass times acceleration. And now,
Acceleration, Part 2.
how do we measure acceleration? That's one way. But there's a better method. You see, most things do all the accelerating they're going to do in a matter of a few seconds. So it isn't very practicable to measure their increases in speed in kilometers per hour. Take this locomotive, for instance. It's a very old steam engine, and it can only do 36 kilometers an hour. But its acceleration is surprisingly good. It can get up to this speed in only 10 seconds. Yes, it is impressive. But can you answer this? How far will it have gone by the end of the first second? Or by the end of 10 seconds? Give up? That's what comes of mixing speed in kilometers per hour with time in seconds. We've got to reduce it all to seconds, and we'd better reduce the kilometers to meters as well while we're at it. The train's top speed is 36 kilometers an hour, which is the same as 36,000 meters in an hour. Since an hour contains 60 minutes, we can divide 36,000 meters by 60 to find out how many meters it goes in 1 minute. Then we divide again by 60 to see how many meters it'll go in 1 second, which comes to 10 meters in 1 second. So we now know that 36 kilometers per hour is the same as 10 meters per second. That means that once the locomotive has reached its top speed, it is covering exactly 10 meters of track every second that goes by, never less and never more. But remember, this is speed, not acceleration. Acceleration means that with every second that passes, the train advances an increasing number of meters until it's eventually moving at a speed of 10 meters per second. But it didn't start out that way. Ready? You've got 10 seconds in which to attain a speed of 10 meters per second. Very good. Now, let's replay that and analyze what happens. In the first second, you reach a speed of 1 meter per second and cover a small amount of railroad track. In the second second, you reach a speed of 2 meters per second and cover a larger amount of track. In the third second, you're going at 3 meters per second and covering yet a longer stretch of track, and so on until by the end of the 10th second, you're going at a steady speed of 10 meters per second and covering 10 meters of track during every second that passes from then on. Your acceleration is over. But how much was that acceleration exactly? That's right. Your locomotive increased its speed by 1 meter per second, every second. In other words, your acceleration was 1 meter per second, which physicists like to write like this. And that's how you measure acceleration.
Eureka!
The story so far. Force depends both upon the mass a thing has and upon how much acceleration you want to give it. Since acceleration refers to rate of change of speed, and since speed can be measured in meters per second, acceleration is measured in meters per second. And now, gravity. If you sit under an apple tree for long enough, this is what is bound to happen. Which is very odd when you come to think of it, since we know that things like to keep on doing what they're already doing because of inertia, because they're lazy. So why did the apple fall down? Aren't apples lazy? This is the problem that puzzled Sir Isaac Newton nearly 300 years ago. The apple was hanging perfectly happily by its stem from a branch of the apple tree. But there comes a time in the life of every apple when it's grown to such a size and such a mass that its stem can no longer exert enough force to hold it up, and it... Hang on a minute. This looks like a tug-of-war. The stem is pulling the apple up, while another force is trying to pull the apple down. What other force? Well, it must be the force of gravity. That's why things fall down, isn't it? Because gravity pulls them down. Yes, but why? What is gravity? Why does it pull things down? That's the question that had Newton guessing until he saw the apple fall and suddenly realized that all objects in the universe attract all other objects to some extent, but to such a small extent that we don't usually notice any movement. But the more mass objects have, the more they attract each other. Yes, we know that the apple hasn't got much mass, but the Earth has. Such a huge amount of mass, in fact, that its gravitational force is enough to attract every single thing that comes anywhere near it, from apples to acrobats, and from oil paintings to green bottles hanging on the wall. Once the force of gravity exerted by the Earth exceeds the force that is holding the object up, down it comes. But just how strong is gravity? Exactly how much force was there trying to pull the apple down from the tree? Well, let's work it out. We know that force equals mass times acceleration. So the force of gravity must equal the mass of the apple, say 100 grams, times the acceleration of the apple. But do falling apples accelerate? Do they go faster and faster the longer they fall? Try sitting under a very tall apple tree, and you'll soon find out. In fact, scientists have calculated that the rate of acceleration at which every object falls to the Earth is roughly 10 meters per second per second. This applies to everything: acrobats, oil paintings, green bottles, and apples, of course. So we can now finish our calculation. The force of gravity pulling the apple down is 100 grams times 10 meters per second per second. And if you want to stop the apple falling, your hand must balance this exactly by pushing the apple up with an equal force. Amazing how complicated a simple little thing like holding an apple in your hand can be, isn't it? Let's simplify it. In honor of the man holding the apple, let's call a force that accelerates 100 grams at 10 meters per second 1 Newton. So that everyone will know that the force of gravity acting on the average apple is exactly 1 Newton. Conversely, that the force needed to hold up the average apple is also exactly 1 Newton. This makes life simpler, and it also shows you that 1 Newton really isn't very much.
Eureka!
The story so far. All masses attract all other masses to a certain extent. The Earth, being a very large mass, exerts a very large force of attraction which is called the force of gravity. This pulls all objects towards the Earth at an acceleration of roughly 10 meters per second. The force of gravity acting on a mass of 100 grams is called 1 Newton. And now, weight versus mass. If anybody ever asks you what a Newton is, yes, you could give them an apple, or a couple of golf balls for that matter, or a small flashlight battery, because all of these have a mass of about 100 grams. And when the Earth pulls them down with an acceleration of 10 meters per second, we say that the force of gravity acting on them is 1 Newton, or that the apple, the 2 golf balls, and the flashlight battery are all pulled down to Earth by a force of 1 Newton. How many newtons are pulling you down to Earth? Well, the simplest way to measure a force is to use a Newton spring scale. If we hang the apple on it, we see that the Earth is pulling the apple down with a force of 1 Newton. And if we hang you on the spring scale, we see that the Earth is pulling you down with a force of, just about 600 newtons. So now we know how much you weigh. What you weigh merely means what force of gravity is pulling you down to Earth. That's all weight is, the force of gravity. Remember how keen physicists are on Latin words? Well, gravity comes from gravitas, which is simply Latin for weight. But you thought you were weighed in kilograms, didn't you? That's true in everyday life, but not in physics, which has to be very careful about these things. In physics, kilograms measure your mass on a balance, but your weight is always measured in newtons on a spring scale. You'll have noticed by now that you can usually work out the number of newtons by multiplying the kilograms by 10. 100 grams, or 1/10 of a kilogram, is about the same as 1 Newton, and 60 kilograms are about the same as 600 newtons. But if 1 kilogram is the equivalent of 10 newtons, why bother to make a distinction between a mass of 60 kilograms and a weight of 600 newtons if they both really come to the same thing? To find the answer to that, let's go to the moon. It doesn't feel as if you weigh so much here, does it? Let's see how many newtons are pulling you down on the moon. Only 100. Why is that? Because the moon is much smaller than the Earth, and therefore has much less mass. So its force of gravity is also much smaller, only 1/6 that of the Earth, in fact. This is why your weight on the moon is only 1/6 of your weight on Earth. What about your mass? On Earth, it was 60 kilograms. How much will it be on the moon? 60 kilograms. Exactly the same, of course. You don't get any smaller by going to the moon. You don't change. Only the force of gravity, and therefore your weight changes. That's the big difference between mass and weight. Wherever you go in the universe, your mass stays the same. Only your weight changes. So if you're not as slim as you'd like to be, don't eat so much. You should join the Mass Watchers Club, because you've got a mass problem. But if all you want to do is lose weight, go to the moon.
Eureka!
The story so far. Mass refers to how much stuff a thing contains. Weight refers to the rate at which that amount of stuff is being accelerated towards the Earth. In other words, weight is just another way of saying force of gravity. An object's mass never varies, but its weight can go up or down depending on the force of gravity acting on it in various parts of the universe. And now, work. These barbells have a mass of 120 kilograms. Since they are resting on the surface of the planet Earth, we know that the force of gravity acting on them is about 10 times that number of newtons. It takes a very strong man to lift something that weighs so much. Because if the barbell is being pulled down by a force of 1,200 newtons, it must take 1,200 newtons of force to hold it up. Of course, if we were on the moon, where the force of gravity is only 1/6 that of the Earth, anybody can do it. But we're not on the moon. That looks like hard work. But how much work? 1,200 newtons worth? To lift the barbell? How far? Exactly 2 meters. But what if you only lifted the barbell half that distance, say 1 meter? Surely that doesn't take as much work as lifting the barbell 2 meters. When you lift the barbell all the way up, you're doing 1,200 newtons times 2 meters worth of work. When you lift it only halfway up, you're doing half that amount of work. 1,200 newtons times 1 meter. In fact, this is how you measure work in physics. Work equals force times distance. Here you're doing 1,200 newton meters of work. And here you're doing 2,400 newton meters of work. That's simple enough. But suppose that after the show, the strong man discovers that his car is stuck in the mud. He pushes it and pushes it, but it won't budge a millimeter. And suppose that at the very same time, the clown, who hasn't got a car, is in the act of picking up the telephone to call a cab. Which of them would you say is doing work at this particular moment? The strong man or the clown? The clown. Because work equals force times distance. And although the telephone receiver only weighs about 2 newtons, while the strong man's car weighs perhaps 15,000 newtons, when he lifts the telephone receiver, the clown is applying a force of 2 newtons through a distance of 50 centimeters, let's say, or half a meter. And therefore, he's doing 2 newtons times half a meter of work, which is 1 newton meter of work. The strong man, on the other hand, may be exerting thousands of newtons of force. But since the car's not moving, there's no distance involved, and the poor man isn't doing any work at all. A force of even thousands of newtons times 0 distance equals 0 work, whereas a force of only 2 newtons through a distance of only half a meter does equal some work, even if it's only 1 newton meter worth. But it's a bit awkward to keep on talking about newton meters of work. So physicists have borrowed the name of a famous British scientist, James Prescott Joule, as the measure of work. 1 joule is the amount of work done when 1 newton of force is applied through a distance of 1 meter. That's to say that 1 newton meter equals 1 joule, which can also be written like this. So the clown did 1 joule of work when he lifted the telephone receiver. And the strong man did 2,400 joules of work when he lifted the barbell. But of course, when he tries to move his car, it's a different story. He does 0 joules of work.
Eureka!
The story so far. Stationary things don't want to move. It takes a force to move them. Force equals mass times acceleration and is measured in newtons. When a force moves something through a distance, work is done. Work is measured in joules. 1 joule is the amount of work done when 1 newton of force is applied through a distance of 1 meter. And now, kinetic energy. Because of inertia or laziness, this billiard ball doesn't want to move. In fact, it would sit there all day minding its own business if another ball were not to come along and knock it into the pocket. Because the second ball forces the first one to move. Whenever you have a force acting through a distance, you know that some work has been done. Fine. But where did this work come from? The second billiard ball, naturally. But what's so special about this ball that enables it to push the other one around? They both have the same mass, don't they? And they're both being pulled down to Earth by exactly the same force of gravity. So what did the second ball have that the first ball didn't? Movement. It was moving and the other one wasn't. And when you have both mass and speed, you have the ability to do work. You can use your movement to get other things to move. In a sense, you have work in you. Physicists, keen as ever on borrowing words from other languages, went this time to Greek and found that the Greek word for in is en, and that the word for work is ergon. When you put en and ergon together, you get energon, which comes out as the English word energy. And the physicists agreed to use this word to mean the ability to do work. So the moving billiard ball had energy. The origin of this energy was, of course, the billiard player, whose arm had work in it, or energy, because of its movement. This energy was transferred to the cue when the arm made the cue move, which in turn transferred the energy to the billiard ball by making it move, and hit the other ball, forcing it to move into the billiard table pocket. In each case, a number of joules of work were done. Arm moving cue, cue moving ball, ball moving ball. But since work is merely energy in action, and there's no work possible without energy, we might as well say that a number of joules of energy were expended each time. And that's exactly what we do say. Both work and energy are measured in joules. Think of joules being transferred from an energy box to a work box, and then to a force times distance box. Joules of energy are spent not only by billiard players, but by hockey players and soccer players, carpenters and ditch diggers. And all the energy to do all this work is only made possible by movement. So that they wouldn't forget this, the physicists went once again to their Greek dictionaries and found that the Greek for movement is kinema, a word that film producers have also borrowed to mean moving pictures or cinema. But the physicists decided to keep the K and to call the energy of movement kinetic energy.
Eureka!
The story so far. Things which are moving have the ability to do work and to apply a force through a distance. They can be said to have work in them. Another word for work in is energy. Since energy is simply the ability to do work, and since work is measured in joules, energy is also measured in joules. The energy of movement is called kinetic energy. And now, potential energy. Once upon a time, a very small man had to do battle with a very large giant. The only thing that the small man had going for him was his sling. When he let loose with it, the mass of the stone combined with its speed to give it kinetic energy, with which it was able to do work on the giant, thereby applying force and exerting that force through a distance. The stone had energy, thanks to its movement. Indeed, everything that moves has energy, even the air around us. Once air is moving, it has the energy to drive windmills. Just as when water is moving, It has the energy to drive water mills. But if every moving thing has kinetic energy, does that mean that things which aren't moving don't have energy? In that case, why are you staring up at that rock perched on the edge of the cliff? Why be frightened of it? It can't have any kinetic energy because it's not moving. And if it hasn't any kinetic energy, it can't do any work on you, can it? But maybe you'd better move out of the way all the same. Why? Because of the rock's position on the edge of the cliff. It hasn't any movement so far, but it looks as if it's on the point of having quite a lot of movement any minute now. Because the force of gravity wants very much to make it fall off the cliff. That means that, in a sense, the rock has a lot of energy stored up in it. A lot of what scientists call potential energy. Or the energy of position. The slightest puff of wind, and that potential energy will immediately start being transformed into kinetic energy. That's how the energy of position becomes the energy of movement. Uh-oh. Don't look now. But it's time to use some more kinetic energy to do some more work on that giant. Whoops. Hold on. What's happening? Let's do that again in slow motion. The stone lost more and more speed as it left your sling because of the force of gravity trying to pull it down. The higher it got, the slower it went, and the less kinetic energy it had. Until at last it came to a complete stop and had no kinetic energy left in it at all. And therefore, no work in it, and no force that it could exert on the giant. But where did all that kinetic energy go? Is it lost forever? No. It's being transformed into potential energy. The work that the little man put into slinging the stone is now stored up in the stone. But of course, in reality, the stone only stops for a split second, and then immediately starts coming down again, until it has got back all the kinetic energy that it had in the first place. Meanwhile, back at the cliff edge, the giant finds all this very amusing. But he'd better watch out, because most of the kinetic energy it took for him to climb up to the top of the cliff is now stored in him by virtue of his position. He's full of potential energy, just waiting to be converted back into kinetic energy any minute now. Timber!
Well, stop your mother and mouth, young